Okay, dear students, so far so good. What comes next is finding eigenvalues and eigenvectors for a matrix of size 3 by 3. So, as I said earlier, here in the discussion of eigenvalues and eigenvectors, we are now going to look for a non-zero vector x, basically a column vector with size 3 by 1, and the scalar number lambda, so that ax can be the same as lambda x. So let's now directly go to, see how we can find that. So first, we have to know that the eigenvalues are obtained using this characteristic equation, determinant of a minus lambda I is equal to 0. So as I tried to explain before, determinant of a minus lambda I is nothing but it is a determinant of the matrix, which is obtained by deducting lambda from the diagonal entries. So you will take the other, elements as they are. So 1 minus lambda, 2 minus lambda, 1 minus lambda, all are labeled here as you see, but the rest are taken as they are, as they are. So remember, students, we have seen how we can calculate the determinant of a 3 by 3 matrix. So applying that, students, you can come across with such kind of output. Basically, what I used is first row expansion. For this, you can have plus here, so 1 minus lambda is used. So delete the first row and the second column, you are left with 2 minus lambda times 1 minus lambda. As you see, minus the product of the two makes 1, so minus 1. So plus, again, when you come to the second case, negative 1 makes positive 1. So delete the first row and the second column, you are left with negative 1 times 1 minus lambda minus 0, because 0 times minus 1 is 0. So for that, you do have lambda minus 1, as you see. So from this, you can have this kind of expression. Students, this expression is called a characteristic polynomial, okay? Characteristic polynomial, but when we equate this with 0, it's going to be characteristic equation, okay? So this turns to be now the following one. Look, from this, try to find the zero values of these three. So lambda equals 1, lambda equals 0, lambda equals 3 are the zeros of this characteristic polynomial. So these are the eigenvalues. 1, 0, and 3 are your eigenvalues. So the corresponding eigenvectors for the obtained eigenvalues are obtained using this one, as I tried to explain in the case of eigenvalues and eigenvectors for a 2 by 2 square matrix. So a minus lambda I times x equals 0 should be used. Here, in place of this lambda, we will have three options. So for each of these three, I'm going to find non-zero vector x so that this can be satisfied. So for lambda equals 1, students, for lambda equals 1, that is to say have 1 here, a minus lambda I is the same as subtracting, 1 from these diagonal entries, as I did here, because lambda is 1 here. So 1 minus 1, 1 minus 1 is 0, and 2 minus 1 is 1, and 1 minus 1 is 0. I'm subtracting 1 throughout the diagonal entries because I'm now solving the eigenvector for the eigenvalue lambda equals 1. So you are left with this, and this is a minus lambda I, students. A minus lambda I for lambda equals 1. Now what about x? X is a column matrix of size 3 by 1, students. A column matrix of size 3 by 1. You may use ABC or XYZ as you wish. Different letters can be used, but it has to be a 3 by 1. If this is a 2 by 1 matrix, this would have been again 2 by 1, okay, x and y, as we did before. Now it is a 3 by what, student? A 3 by 1, so you need to have x, y, z, and this needs to be equated with 0, because this is a column matrix, a column vector, okay? It's not an arbitrary number 0, because we don't have determinant here, okay? So this is 0, 0. Now let's multiple. When you multiple this by this, look, 0 times x is 0, minus 1 times y is minus y, as you see, and 0 times z is 0, so you are left with minus y being equated with 0 with this one. Again, minus x plus y minus z. Minus x plus y minus z is equal to 0, kanka. And from this, students, z is going to be what, student? Because 0 is already obtained here. So z is going to be equal to minus x. Z is minus x. How about here? X is 0, y is minus 1, z is 0. So y minus 1 equals 0 is y equals 0. So students, the eigenvector is basically a 3 by 1 matrix. So x, y, z. As you see, it's labeled here, x, y, z. So x here, what is y? Y is 0, as it is stated here. And z is minus x. So I'm writing everything in terms of x, but you students are able to write in terms of y or in terms of z as you wish. Now look, x0 minus x. This shows you that you are free to use any non-zero x value in place of what? In place of lambda, so that this can be satisfied. For what I mean, for in place of x, for lambda equals 1. Okay, lambda equals 1. Our intention is to find x equals lambda x. So for lambda equals 1, you are free to take any non-zero x value, so that you see x0 minus x can be used in place of x. For example, 2 0 minus 2 can be used. 5 0 minus 5, negative 5 0 5. You are free to take 100 0 negative what? 100. 1 over 2 0 negative 1 over 2. You are free. So take x as a common out, and then you are left with 1 0 minus 1. So x needs to be different from 0 because you are looking for a non-obvious or a non-trivial student, a non-trivial solution. So every other vector is obtained by taking a multiple of this vector. So x1 can be 1 0 minus 1. So your eigenvector can be the vector with components 1 0 and minus 1 for lambda equals 1, right? Now we're not finished yet. We do have two other eigenvalues. So for lambda equals 0, what's going to come, students? For lambda equals 0, look, student, you have to put zeros throughout here in place of lambda, or deduct 0 within these diagonal entries. So 1 minus 1 0, look, minus 1 2 minus 1 0 minus 1 1. When you deduct 0 from whatever entry, the entry comes as it is. So just take matrix A as it is. Then you see you are having this vector, and this is equated with 0 0. As usual, you have to operate this. 1 times x is x, minus 1 times y is minus y, x minus y. Do the same here. Minus x plus 2y minus z, students, is equal to 0 can come. And finally, minus y plus z equals 0 can come. Here, clearly, you can understand that z is the same as y, and y is the same as x. If z is the same as y and y is the same as x, you're having here y is the same as z is the same as x. So the eigenvector is going to be x, y, z. So we can write everything in terms of x or y or z as we wish. Since x is x, y is the same as x, in place of y I took x, z x. So dear students, you are free again to use any non-zero x value here, you see, as one possible eigenvector. You are free to take 100, 100, 100, negative 2, negative 2, negative 2, 1 over 2, 1 over 2, 1 over 2, radical 2, radical 2, radical 2. Am I able to list every real number? How could I do? Take any x, a number different from 0, as a coefficient out, and then you are left with 1 1 1. So instead of considering this, take one possible eigenvector standing for all, so that is considered to be the base. So you are free to take 1 1 1. So your second vector, your second vector for the eigenvalue lambda equals 0 is this one. And coming to the last one for lambda equals 3. Students, again, you need to deduct 3 from these diagonal entries. That is how you can find a minus 3i. Lambda now is 3. This is a governing one. So 1 minus 3 is minus 2. Look there. 2 minus 3 is negative 1. Look. And 1 minus 3 is negative 2. What about the rest? They are written as they are. Then you take x, y, z. This is your vector. Then this needs to be 0, 0. Then from this, multiple again as we did before. Minus 2x minus y 0. Minus x minus y minus z 0. Minus y minus 2z 0 can come. And from this, y is 2x. Just move this minus y to the right. Y is negative 2x. And here, y is, students, y is negative 2, what? Z again. Okay? But we knew what z, just substitute x, y, x, z, and try to write z and y in terms of x. So y is minus 2x. If y is minus 2x, now z can be obtained. Simply substitute in this third equation. So you will finally obtain, you see, x, y, z as x minus 2x, x. So as I did before, take x as a coefficient out. So you see 1 minus 2, 1 can come. For every non-zero number x, you can have these possible eigenvalues. But as I say, the simplest case is taking this vector, because every other vector is obtained from this combination, linear combination. So 1 minus 2, 1 can be taken. So the eigenvalue corresponding to this lambda equals 0 is x3, as it has been stated here.